Hello, here we're going to look at the 2.4 through 2.5, and for level 3, 2.6 practice quiz. So I'm just going to go through and quickly explain the answer key here. So for this first one here, we'll see what key features we use to sketch this graph. Just starting with A, you look at it and it says a continuous and symmetric about the point. So this is point symmetry, which we didn't put a big focus on. But you'll see in example B, I have crossed out that it's definitely not line symmetry. If you look at that big green line, it's definitely not symmetric about that line, but it is if you rotate it, and I kind of extended the picture to help you see it, it does have point symmetry, which once again we didn't cover too much because it's just kind of a visual thing, and in this case they told us, look for the point symmetry. So we did, there it is. And the other components match as well, such as the y-intercept and the ending behavior, because as this travels to the left, we point down, and as we travel to the right, we point up. We see that that also matches on the picture. All the other answer choices would have something wrong with them. So, number 2, a banquet hall has tables that can seat 8 people. The number of tables needed depends on the number of guests. What type of special function models this situation? This is a step function, because you need a table for however many people, and then all of a sudden, if a 9th person shows up, you need a whole new table until enough people fill that, and then you'll need a 3rd table. So that is a step function. Identify the range of that y is equal to the absolute value of x. This is that V-shaped graph. This is what the absolute value of x would look like. The range is all possible y values. So this one here, if you take a look at it, we never reach any negative y values. It stops at the origin. So the range could be described as that all y values must be greater than or equal to 0. For questions 4 and 5, we're going to use this chart, this graph. It says, which statement is true? This one is not point symmetry. This one is, in fact, line symmetry, to where it's symmetric through this line, to where each side of the curve could kind of look at that line and see its reflection in the mirror. The end behavior, remember as x approaches negative infinity, that's our left arrow. Our left arrow is pointing up. As x approaches positive infinity is the right arrow, which our right arrow is also pointing up. Number 6, using this graph here. I went through and checked off things that are correct, but marked off things that are incorrect. B, all the different pieces are correct. All of them have some things that are true, but B is the only one that where every single thing that they list is true. Now, they don't necessarily talk about every single component of the line, but B has the one that has everything they mentioned based upon the graph is accurate. Seven, identify the type of special function. When you see those bars straight up and down, that's an absolute value. It's the way it's always been, way back since your times in Algebra 1. For this one, number 8, it says, which is not part of the definition of the piecewise function shown. I drew arrows connecting each part to the correct segment. The only one that is not true is the one that's highlighted there. That equation is not shown. If it was shown, it would be something like this. Y-intercept of -3, slope of up 1 over 1, and you can see that nowhere on there do we have that line. So it is H. For number 9, we're just looking through. This one is not point symmetry. Remember, point symmetry would be something kind of like a fan blade to where it can rotate around and be balanced. This is line symmetry, where it's symmetrical on both sides of the line. So you'll want to be prepared to make some sketches. There may be some that are multiple choice. There could be some that are multiple choice as well, though. So I was going to sketch these out here with you on this video. So the way you do these is you use the information they give you. For this first one, which is an easy sketch, the x-intercept is 5. And it says the y-intercept is 2. And then when it says the function is decreasing for all values of x, that means we have a negative slope. So that's actually enough information to go ahead and connect those with a line. The rest of the stuff just automatically becomes true. As we head to the right, we're pointing down. As we head to the left, we're pointing up. You can see that that is true on our line. Here's a medium difficulty sketch. The function is continuous and symmetric. The symmetric part's important. So we're going to be symmetrical about the line x is equal to 2. It says the function has a minimum at 2, -3. All right, and then it tells us as you head to the right, you're pointing up. So I've got an in behavior up. As you head to the left, you're also pointing up. So we could make the straight lines, we could give it curves. As long as it is symmetrical through that line, that's what you need to get credit. Symmetric through that line with a minimum at 2, -3. This one is a hard sketch. We have a y-intercept at -4. It says the function is continuous and positive. So this means that x of -3 and x of 2 are x-intercepts. And it also tells us that when we are to the left of -3, we're above the y-axis. And when we're to the right of 2, we're above the y-axis because they told us that the function is positive. It tells us that the function has a relative minimum at -2, -3. So there's a relative minimum. And it says the function is increasing from -2 to -1. Well, we know the relative minimum has to have something like that for it to be a relative minimum. It's the bottom of a hill. And they let us know that, hey, I'm increasing. So this hill here will continue to increase until it gets to x of -1. All right, which means somewhere on that line, and it could be anywhere, as long as it is above that relative minimum. So now anywhere on that yellow highlighted line, as long as it's below the x-axis, because we can't have any new x-intercepts, we had to turn around. Right, and that was just implied by the information. It was implied by this part right here, that we were increasing on this segment here. I'll draw it in blue. It says that that segment's increasing until it reaches the x-coordinate of -1, which is that yellow line. So your point could be a little higher or a little lower. It's all the same because it's just a sketch. And our ending behavior is true as well. As we head to the right, we're pointing up. As we head to the left, we are pointing up. So this part here is for the level 3 only, 2.6, describing the transformations. Recall when you have a unit inside the absolute values or inside the parentheses, it's a horizontal movement, and it does do the opposite of what you would expect. So this is +5, which makes you want to say to the right, but it's actually to the left. For number 10, a reflection means we need a negative sign. And we also need to keep our same parent function. So this one's out because it's not a negative sign in front of the x squared. This one isn't the same parent function. It's not x squared. It's a trick answer. This one has a coefficient, but it's not negative. There's our negative with our x squared. Dilation is having a coefficient greater than 1 out front. So 2 is greater than 1. But our parent function is just y is equal to x. This is x squared. This is -x. That would be a reflection. This one would be a vertical shift down 9. This one is our dilation because we have scale factor of 8. For this one here, we have a number on the outside that's a k value. It shifts us up or down. It's not opposite like horizontal movement is. So this is a vertical shift up 5. Also level 3, be prepared to look at and think about and potentially graph a greatest integer function.